start recording, so other people may be able to watch this again. If any question, you just ask, okay? Okay, let's start with the definition of momentum inertia. Typically, people use this letter I to represent the inertial momentum. And how this comes from? Okay, let's recall that the kinetic energy K is equal to half mv squared, right? So this is for just one point mass. Or one mass, okay? I don't have to say point mass, okay? So if you have multiple mass, how that goes? The total should be sum. Okay, let's say we have 1, 2, 3, 4, 5. I equal to 1, 2, 3, 4, 5 to any numbers to n 1. Okay. So the total kinetic energy should equal to half m the I mass times the velocity of the I mass. Okay. Now we want to apply this to the rotational system. Rotational system, something like this. Okay. So let's say this is the point, center point O, and this is a mass. Let's say mass I. This is another point here. Mass. Okay, let me do this way. This is mass 1. This is mass 2. And the distance from the mass 1 to the center point, let's say, is R1. Okay, and for this one, R2. This one, okay, I should just use tiny circle. Okay, so this is mass n, and this radius Rn. Okay, and let's say the system rotates with some angular velocity, omega. Angular velocity, something that rotates counterclockwise, omega. So when the system rotates, each point will have some like speed, right? And the one you close to the center or the center, the smaller you have, the smaller with speed that you have. And the further away you from the center, okay, maybe you cannot see this. You can rotate faster because the entire system, when they rotate, they have a common angular velocity, omega. And we did this some other labs before. So for a rotation system, for example, we say that in like a spring, a simple pendulum, this is theta. Okay, and we try to determine the relation of this is R, this is some mass, pendulum mass here, or some velocity. Recall that the velocity for this case is velocity should equal to R times the angular velocity dot. So when I say theta dot, this is defined as d theta over dt. So it's how much the angle change. Okay, this is angular velocity. Is that clear? Hello?
Yeah.
Okay. Yeah. Okay. I just make sure you are listening. Okay. So here, the angular velocity here we represent as omega here. Okay. Remember, this is how much angle you travel over time. So for each of these points, they have velocity. For the M1, its velocity is omega R1. This is V1. Okay. So for the V2, is omega R2. And for any other point, it's just like in proportion to the distance is from that mass to the center of the rotating system. So this is Vn should equal to omega Rn. Okay. So now we can apply this to, can compute the kinetic energy of the entire system. It's just equal to, copy here. So K, from the original definition of kinetic energy, half I V I squared. And now, in the rotational system, the V can be replaced by R times Ri times omega. Okay, here I use the lowercase, so I can use lowercase here. So this is equal to half I Ri square omega square. The thing we want to notice is that here, for rotation system, any point in that system will share the same angular velocity. So because they rotate in the same rate in the angular direction. So there's the common factor here. So we can factor this out to get half omega square and sum over all the mass I and Ri square. So you can see that this term here, this part here, is the definition of the inertial momentum in your textbook. So let's define this equal to I. Okay. So then we can simplify the kinetic energy as half omega square. So to define the inertial momentum, it's just to make the calculation on the rotational system much easier. Okay, you can still using the ordinary definition to do that, but it will be, you see, you have to compute like you have to sum up all the mass. If the system is continuous, for example, like a disk, a continuous disk, you need to do integral. So the summation here, I equal to all the point mass, Ri square. Okay, someone is coming. Hello? Hello, we just started about how many minutes? About 5 or 10 minutes. Okay, I will post this. We are recording the meeting here. I will push it out to the YouTube, so you can watch that later if you miss anything. So this is the summation. When you have some like discrete point 1, 2, 3, 4, 5, you can count. You can use the summation to compute the inertial momentum easily. Equivalently, for example, for a continuous system, like a disk. Okay. And if you have different center, you put the center here. Then you need to do the integral. Each point have different distance to the center point here. This is equivalent to do like Ri square. Okay, each point. So each point, we define the integral variable as R, each point here. And let's say this system has a density of rho. Okay, so you need to do this R square each point density times what? Density show times d v square. V is the volume, tiny volume. So in this case, if we assume the uniform density, you will get something like this. I made a mistake. dv is like, for example, for 2D, dv is dx dy. Okay, 2D. dv equal to dx dy dz in 3D. Okay. So for different dimensions, you have different volume of integral. So this is how you get that. Some of you ask why we need to do integral. This is when you try to treat the continuous system. That's what you need to do. Okay. So now let's come to so this is the definition. Then realize that I just write down the conclusion here. For the general system, we have kinetic energy can be written this way, or a mass, single piece of mass that is not rotating. You can V squared. And for a single piece of mass that is rotating around some axis, you can compute this way, I omega squared. Omega is the angular velocity. So you look at this, the mass here is equivalent to the inertial momentum. Okay, so the inertial momentum is something equivalent to the mass in the regular system without rotating. And the angular velocity is something corresponding to the regular speed in the ordinary system. Okay, so this is rotating system. And this is something we're familiar with. Okay, so when you every time you come to like rotating system, you just need to figure out the angular velocity, and you think it's not a momentum inertia, and then you treat that as a mass. And for the velocity, because it rotates, so you use the angular velocity. Okay, so then the other formulation is just the same as regular system. For example, like the momentum we have, the regular momentum is defined as mv. Okay, and the angular momentum m will replace m by I, and v by angular velocity. So, and for the force, every time we force here, force can change the momentum. And in the angular velocity case, you do like the unit analysis is something called torque. The force times R. For example, you have like something here. This is a rotating system. Force corresponds to something like this. What we are going to do is the force. There's more mass here, mg. Okay, and this system, this is a wheel. In the online assignment, it's wheel that can rotate. You release the hanging mass here, it starts to rotate. Okay. So this has some inertial momentum, I, we are going to figure out. And to figure out another thing that means here, so K have the same definition here. And for acceleration in the regular system, we have some acceleration in the angular velocity. Yes. This is equal to d angular velocity dt. This is the angular velocity acceleration. It's equal to the d theta over dt squared. So the theta here is like the displacement in the regular system. Okay. So here you want to figure out like the inertial momentum of the system we are going to work on in the online assignment. We want to figure out I here. We need to figure out how the angular velocity, because Newton's second law in regular system, ma, in a rotating system is F times the R is the torque equal to mass here is inertial momentum. A here is the angular. A here is the angular velocity acceleration. Okay, so this is how much the angular velocity change. First, we need to compute this in the experiment. We need to figure out. For example, we have three time t1, t2, t3, 3 time points, and the system rotates from the t1. Let's say, okay, we have a circle here. We have mark here, okay? This is T1. Let's say at time T2, it rotates from here to here, okay? And then at T3, from here to here. Let's say this theta 1, this is theta 2. Okay? Then you can compute the velocity in the regular system is equal to S1 minus S2 divided by T1 minus T2, right? The time difference. So, or is equal to ds over dt. This is the definition of the velocity. Similarly, the angular velocity here, let's say angular velocity here at this point, at this region. So at this region, we have angular velocity 1, angular velocity 2. So angular velocity 1 here in that section is equal to theta 1. Theta 1 is the change of the angle divided by the change of time from here to here, T2 minus T1. Okay? So you can measure the angle, how much the angle change, use the protractor to figure out how much angle change during that small time interval. And the angular velocity at time 2 is theta 2 over T3 minus T2. Okay? So, and then we can compute the velocity change. They say the average velocity at this point and average velocity at this point. So angular velocity 1 is the average velocity during this time, and it's another color. Okay? And the angular velocity is 2 is for this part. And so the angular velocity acceleration should equal to the change of angular velocity, W2 omega 2 minus omega 1, divided by the time difference. Let's say this is 1 second, this is 1 second. So from 1 second to next 1 second, the interval is 1 second. So it should equal to T, let's say T, okay, here, funny. T0 is equal to, T1 equal to 0, T2 equal to 1, T3 equal to 2, okay? So T1 and T3, here's one second interval, here's one in, oh, I forget that, you cannot see my finger. So from T3 to T1, there's one interval, 1 second interval. From T2 to T1, this is another 1 second interval, okay? So during this time, the angular velocity change is just the middle point here, from this point to this point, because we take the average when the time is very small. So that is also 1 second, 1 second. You cannot just count from the boundary from here or here. You have to count from the average, okay? So we assume that this theta 1 and theta 2 is very small, so you can compute that very accurately. You pick a very big angle, the average will change a lot, okay? So we don't like that. So you can compute in this way. You can, and this is equal to, once you know the angular velocity, you can get the number from the online interactive, like the figures on that. I will show you later. So then you can use this formula here. F here, R equal to I omega 1. So now you know this. You know this. You know the force here is G. Is the Hanning mass. Hanning mass here. Okay? And R is the radius from this point to this point. This is R. This is the torque. Okay? So with this torque, everything can be measured. You can measure this thing and this thing. Then you can get this thing. So the only thing I know is just this part. Okay? So this is the theory and how the inertial momentum comes from. And now I'm going to show you how to do this online, because some of you don't know how to play with that. I also tried to figure that out, but now it seems it's not hard. Okay, so I will share another screen. Oh, where's that? One second, I need to find online. Oh, here. I will change the screen 1. Okay. So can you see my new screen?
Yes.
Okay. Thanks. So let's work on this together. Where's my class? Okay, here. Rotational system. Oh. Okay, so I just picked the random one. So how we do this? So here there's one table, okay? And yeah, the student maybe not do this in the right way. Okay, so how we do this? You see there's like a tool here. You can have time. And you can also have the protractor, something like this. Okay. The protractor is not like it's have not like tiny like one degree, 2 degrees, something like that. But you can count from here. Can you see that my cursor here? This point to this point and to this point and to this point. This is how many degrees? 90 degrees. Okay. So you can, like for example, I just said in the notebook I did, you can pick this as original point, and then you figure out how much time it takes from this point to this point. You can use the timer, okay? So let's do this. So when this guy like cut this line, you can stop. So you can figure out what the time is, how much time it takes by jog this progress bar here. So see, it takes 1.15 seconds from here to here. Okay. Then you can figure out the angular velocity should be equal to, this is how many degrees? 30 degrees. 30 degrees is how many? In radius should be pi over 6, right? So you can compute that. So pi over 6 divided by how much time? 1.15 seconds. Then you will get the first angular velocity, omega 1. Then you let this run again, so it will travel from this point to the next mark here. You can fine tune this. Okay, so it's 1.15 seconds. That means the time it takes from this point to this point is 1.5 minus the previous time. You see here, the previous time here is 1.115, okay, something like that. You can use like left and right key on your keyboard to fine tune this to get accurate results. So for the first 30 degrees, it takes 1.15 seconds. And for the second 30 degrees, it just takes how much? Okay. It just takes 1.5 minus 1.15 is 0.35 seconds. So the rotating acceleration is speeding up. Okay, then you can compute omega 1 is equal to 6 pi over 6 divided by 1.15. And omega 2 is equal to, I hope I can share, okay. I can share the screen with my note. Okay, so I will repeat that on my tablet, okay? 0.35. Then you get omega 1 and omega 2. And the time is traveled from here to here. Okay, let's say from here to here is like about point. So at this point here, the average is about, let's say here, okay, I'll rotate this one. So the average is because this has some interval, finite interval, we want the average. The average typically is at the center point here. Okay. So this is at this point, this is the angular velocity at this point is the one we just computed. It's the omega 1. Then it was third to this one, next to the center point here. Okay. So if I write the time here, it's 1.38, and in the previous center point here, it's 0.95. So the acceleration time from omega 1 to omega 2 is about 1.38 seconds minus 0.95 seconds. Then you can compute the angular acceleration is equal to omega 2 minus omega 1 divided by 1.38 seconds minus 0.95 seconds. Okay, I will show you on the tablet. I will switch the screen. Yes. Okay. I just changed to this, write down what we just discussed. So we have a setup like this. We have 3 points here, 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 here. So we have 3 intervals here, 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 here. Okay. I just write down the number here. So from here to here, the first section, when we rotate, this is a mark. Okay, the point we track. So from this point, the first point to second point, the travel, the angle 1 is pi over 6. Okay. Pi. My writing is terrible. And the time it takes is 1.15 seconds. Okay. And from the second part, second theta 2 is also pi over 6. The time it takes T2 is just 1.5 seconds, because here at this point the time is 1.5 seconds. Here is 1.15 seconds. Here 0. Okay, this is the beginning. So you can figure out the time difference. So the T2 is the interval here. Okay, minus 1.15 is equal to 0.35 seconds. Okay. Then we can compute the average angular velocity at the first section, angular velocity 1, angular velocity 2. So based on the differentiation, like the average velocity, it should be 6 pi divided by T1. Okay. And you can compute this. You have the calculator, you have the data. And the angular velocity 2 is 6 pi over 0.35. Okay. T2. Okay, you can do that. You just plug in the number by yourself. Okay. And the last part, because this is the velocity change from this section to this section, and this is the average with angular velocity at the first section. This is angular velocity at the second section. So this average velocity corresponds to the center point here, because average, right? And I check how much time it takes from here to here, from this blue dot cross to the second blue cross. So from the first center part to the second center part. Okay. And I figure out that the time here is, the time point here is 0.95 seconds. And the time here, time at this second point here is 1.38 seconds. Okay. So the time it takes to accelerate from this point, the center point here, Hey, can you see the cursor? I didn't see the cursor on the share screen because I used a pen. Okay, I should try it. This is very inconvenient. So from this point to this point, the time it takes to accelerate is equal to 1.38 minus 0.95 seconds. Okay, so this is equal to how much? 0.43 seconds. And we know the angular velocity, angular acceleration is the change of the angular velocity. So it should be angular velocity equal to delta of angular velocity divided by the change of time. Should equal to angular velocity 2 minus angular velocity 1 divided by delta t here. Any questions? No? Okay. So now from this, you just plug in the number and you can get the result, the angular velocity. Okay. And if you use the Newton's second law for the rotating system, we have I is the mass, okay, times angular acceleration should equal to the torque. Torque is equal to F force times the R. The force here, we have the force here is we have a circular here. This is the center point. So the force is equal to mg, okay, times r. R is the radius of the bicycle wheel. And this is not very strictly because the tension actually should talk how to, okay, let me do this. So the actual force is the tension on the string. The tension typically is not equal to mg. It should be smaller than mg. But as long as the acceleration is small, when we see that this mass, when the mass is much smaller than the big mass here, we can approximate the tension is roughly equal to the mg, because when you see the acceleration is equal to, I mean the acceleration for this one, A is equal to mg minus t, okay, divided by m. This is the net force. So if A is very small, when A is very small, A close to 0, this term is close to 0. In that case, T will close to mg. Okay. So I made a mistake here. It will be T times R. So the torque is the tension on the string times the R. Okay. But the tension, when you know that the wheel is rotating very slowly, that means the acceleration is very small. So A is very small, roughly like constant speeding, constant velocity. So we can cheat this as some approximation. We can do this in more like using conservation of mechanical energy as stated in the lab manual. In that case, we can get a more complicated formula. It's also doable, but we don't want to go that complicated because, yeah. So we use that approximation. We assume the acceleration here is very small. Okay. So the tension is roughly equal to small mg. And now let's go back to the, I think this is given, this number, the mg is given in the, yeah, the m is here, 20 grams, okay? Equal to mg times r. So move this away. So our discussions. Equal to 0.02, this is in kilogram, times 9.8 meter per second square. This is G, and times R. What's the R? R. What is R? We don't know R. We know the R? No, we don't know R. Okay. So we don't know the R. The R can be measured using a ruler. Okay, I'll go back to another screen. Yes. Okay, can you see? Okay, yeah, you can see the new screen. So here, there's like a button you can click to have the ruler here. So you can use this ruler to measure the radius from 0 to the center. It's 30 centimeters. So the radius R is 0.3. Okay. Okay. Then I will come back. So now this is 0.3 meter. R equal to 0.3 meter and equal to 0.2 kilogram. Okay, G is given. So here you can get this. This is from the top. You can get angular acceleration. Then once you know the right hand side, you can compute I. I is just trivial. And G R divided by angular velocity. Okay, this is the formula we can use to calculate the angular velocity in the angular acceleration in the assignment. Do you have some other questions? Oh. Hello? Hi. Are you here? Or you just run away? Okay, no questions. Good. So now you know how to do this, right? It's pretty. Okay. Okay. Yeah, and for the future sections, if you need any, we can schedule similar meetings if you need any explanation. Okay. That's great. Okay. Thank you all. Yeah, see you next time.
Thank you, Mr. Huang.
Hey, 谢谢，拜拜。
拜拜。
Thank you.